Hello, this is Diego. In this tutorial, you will learn how to analyze developable structures using Karamba. First, we will learn the reverse engineering process of simulating the conditions that make a developable structure try to recover its original shape. And then, we will apply this approach to analyze an already assembled developable structure so we can get some interesting feedback from our design regarding the actual shape that our structure will eventually have, or even if our sheets are strong enough to resist the folding forces that result from a particular geometry, which is information we might want to know before actually getting into building the developable structure. So let's get started. Let's start with this simple linear problem. So here I have basically a circle and I've just removed the final piece so that the endpoints are not connected. And what we are going to do is to simulate a sheet of poplar wood with this shape that tries to get back to planar again. So let's start as with any normal Karamba model with the assembled model component, and I like to start this way because here we can see all the inputs that our Karamba model requires. So let's start with the elements, and since we are dealing with a linear problem, we are going to use the line to beam component like that. So first, let's reference our geometry in Rhino. And first, I need to transform this curve into a polyline like this. And of course, I need more segments. And now I need to break down this polyline into the individual segments. So let's explode this polyline like this, and perfect. Here we go. So these are my elements, and of course now we need to define the cross sections of these elements, and for that let's grab the cross section component, and here we have many different options to choose from, but in this case we are going to use trapezoidal cross sections because we are going to simulate a sheet of poplar wood, and that's the best approach to go. So now let's define the material for this cross section, and I've already looked up the properties of poplar wood in Google, so trust me with this one, please. I'm just going to copy this material here with already defined parameters regarding the Young modulus and also the strength of poplar wood regarding tension and compression. And very important, pay attention to the units that Karamba requires for each parameter. So let's connect this guy, and now we are ready to define the dimensions of our sheet of poplar wood. So let's use 1.5 centimeters for the height and 120 centimeters for the width. Like that. Fantastic. Okay, this is my cross section for my elements, and since we have many different elements, it might be a good approach to define identifiers for each and any of them. So let's use the length component. So how many segments we have, and we are going to take a list of numbers as identifiers. So let's get the range component. Perfect. And now I need identifier, and I need to concatenate this. So like this, separator underscore. So these are my identifiers. It looks that like it's working good for the moment. Okay, so those are my elements. And now let's go with the supports. So this is very easy. Let's just take the start point of this curve, and we are going to fix all degrees of freedom like this. Okay, perfect. Oops. So that's great. And now our model is not finished yet because we have to define the loads. but we can already visualize how it looks like. So in order to visualize it, we have to use first the model view component, and since we are dealing with linear elements, we have to combine it with the beam view component, like this. So, of course, we cannot start displaying deformation and so on, but still, now we can see how our cross-section and or even our structure looks like. So it seems like it's working so far. And now, well, now it could be a good point to save the grasshopper definition. And now let's define the loads that make this structure try to get back to planar again. And for that, let's get the loads component here. And what we are going to use is the initial strain loads. And we are going to use initial curvature that tries to get that planar again. So as a short introduction, you can go to the Wikipedia and you can see the definition of curvature. And in this case, since we have a circle here, it's going to be constant for each element, and it's basically the reciprocal of the radius of this circle. So if in this case I have a radius of 0.5, so my curvature should be 2. So let's check that out. And yes, this is my curvature, but here I'm getting a vector, and I don't know if those are the right coordinates to apply this curvature into the Karamba model. So, of course, when we are not sure how to go on with that, we have to check the Karamba manual, and in this case, under loads, you can see that this explanation says, okay, this kappa input is a vector of curvatures, and yeah, basically, we have to apply this value as a rotation about the corresponding axis. So first we have to visualize the local axis of my elements, and for that I have to use the disassemble element component. So step by step, those are my elements and those are my local axes, which are defined as planes, like that. Okay, but that's not very easy to visualize, so let's take the list item component, like that. Fantastic. And now we can see, hopefully, now we can see that yes, so this is, for instance, my local axis for this element here, and we want again we want to make this planar again, so we want to apply curvature around this green axis, and green means y, so this is the axis that we have to use. And also it's important to take a close look into this, because you can see that for these elements the green axis, the y-axis, is pointing in this in the left direction, and now here is pointing to the right. So we have to take that into account in order to apply the curvature with the right sign. So step by step, first let's get the basically let's take the numeric value of this curvature. So of course length, vector length. Okay, this is my curvature, fine. And as I said, we have to apply it into the y component of a vector. And now we are not done yet, because we have to take into account this direction of the local axis. So for that, reconstruct plane. Yeah, fantastic. And no, but I don't want these guys anymore. So first let's take the y-axis, of course, and we are going to multiply that guy, deconstruct vector. So basically here in the x component I'm getting values of 1 or -1, depending on whether this axis is pointing to the right or to the left, and we are just basically going to multiply those values by our curvature here. Okay, and that should be it, basically. and I also have to do it like using negative values in order to work the way we want, because we want to get this planar again, not to fold it more. So let's use the negative component for that. Fantastic. And now it should work, it should be working, but we are going to add another factor to this multiplication, which is going to be basically a scale factor to try to follow better this folding process. So let's define a scale factor between 0 and 1, like that. And now we have finally our curvature vectors here, and as I said, in the y direction, because that's the local axis that we have to focus on in this case. So this is my curvature vector, and now let's use our identifiers also. In this case it's not that important because we are applying the same curvature in each element. Well, actually it's important because we have this problem with the local axis that it's pointing in the other direction, so it's actually good practice to use identifiers. And now, since I want to use different loads for its element ID, we have to graph these inputs. That's right. So now you can see that, and of course we have to flatten our output. So now you can see that, yes, we have a different load for its element ID, and we are ready to plug this load output into our assemble model component. And of course nothing happens because we have to analyze our Karamba model. And this is a perfect problem for the large deformation analysis, because the deformation is going to be large, as we are going to see. And here the most important parameter, of course, besides the model, is the number of load increments. So since this is a very delicate problem, I can tell you that we are going to use 200 iterations at least. Okay, so now let's plug our model here. It seems like it's working. We can get the displacement here, 77 centimeters, so yeah, that's actually a large deformation problem. And let's see how it looks like. Okay, so I'm sorry, I forgot that I have to use not this parameter, but of course the local coordinate system as input for our local axis. So now, once I fix that, I can see that, yes, that basically our folded sheet of popular good is back to planar again. And if we want to, we can use this scale factor to see properly how this folding or unfolding process takes place. So it looks like it's working properly. Okay, and now let's try to apply this approach to our assembled developable structure that we can see right here. So let's start like before with the assemble model component. And now, since we are dealing with, let's say, surface elements, we have to use, instead of the line to beam component, the mesh to shell component, like that. And of course, now we have to reference our geometry in Rhino. And I like to use the wireframe mode to see better what I have already referenced. So what we have to do when we are dealing with surfaces in Karamba is to mesh them. And for that, the best approach is to use the mesh breadths component from Karamba. And why is that? You are going to see that in 1 second. So basically this component is very powerful. Let me just use a higher resolution for our mesh. Because if you take a closer look into it, into this geometry, you can see that Karamba is meshing all the faces of this pre-rep so that the points are coincident for the elements of different faces. So if you take a closer look, perhaps I should hide this right here. So you can see that this node is the same for the faces of this, for the elements, sorry, of this face and of the neighbor face here. And this is really necessary if we want the simulation, to work later on. So now we can see that our mesh looks nice and we can move on. So this is our mesh, but we are getting different, so one mesh for each face, and actually we have to break them down into individual meshes with just one face each one, because we are going to apply different loads or different curvatures into each one of them. So in order to break them down, let's use this, yeah, that's right, let's do it this way, face boundaries, and let's create a simple mesh from each of these faces. So like that, and that's right. Now we can flatten this input, and these are our elements. So again, as before, now we have to define our cross section for our shell elements here. And let me grab the material state property of our poplar goods from our example before, like that. And now we are going to get the cross section component as before, but of course, since we are dealing with shell elements, now we have to use the shell constant cross section type instead. So this is my material, and we just have to define the height, and let's start with 1 centimeter. Okay, perfect, and that's right. And now we just have to define the identifiers for our cross sections in order to apply different loads to its element. Identifiers for our shell elements. So here we go. Now I have to flatten this guy, and hopefully that's right. So, but instead of using this keyword, we are going to use mesh as identifier. So okay, perfect, I think it's working. Let's connect these guys here, and now we are done with our elements. So let's move on to the supports. Fantastic. So now in this problem we are just going to be dealing with internal forces. So we are not going to get actual reaction forces here. We just need one support, so we can fix our model, let's say, and the Karamba solver can work and can get the solution of this static problem. So we are just going to use one random point of this mesh. Let's just deconstruct our brep here, and let's sort these points, and let's get the first one of this list, so it's more clear which one we're using. But again, we could use any vertex of those meshes. So this is the support that we are going to be using. Okay, perfect. And now we are done with our elements and with our supports. And as before, now comes the most complicated part, and it's of course how we're going to apply our loads, or better said, our curvatures, into this geometry or into this model. So let's get the load component again. So first, what we need to do is to get the curvature value in each point of this surface, and that's the value that we have to apply into our Karamba model, but of course with the negative sign, so that these surfaces try to get back to planar again. So again, let's try to get these curvature values, and of course for that we have to use the principal curvature component. That's right. So the input of these components are going to be the faces of my brep, which I have to graft for later on. And now I need to get the UV coordinates for the points in which I get to get the coordinates. And of course, these points are going to be, let me hide this guy, and this guy, and this guy. Okay, so these points are going to be the central point, let's say, of its mesh or of its face. And in order to get those coordinates, let's use the closest point component. Surface closest point. I hope this works. So these are my faces, and I have to grab them again. And now I just want to get the central point of its face, and that should be not complicated. Okay, those are my points, so I'm getting the UV coordinates here. Fantastic. And now I'm using the same structure, data structure, as with these faces. So now it should be working. Let's just check which values we are getting. So the principal curvature is C1 here, and okay, those are the values that we are getting. Again, it's not such a strong curvature as in our previous example, which makes sense because our sheets of poplar wood are not that folded in this case. And we can check the minimum curvature, and of course it's 0 in each point of our geometry, and it makes sense because since we are dealing with developable structure, the minimum curvature has to be 0. Okay, so that's everything regarding our curvature values. Now we can flatten these guys, and now it's get complicated. So I'm going to save my grasshopper definition. So now what we have to do is, again as before, apply these curvatures regarding the local axis of our shell elements. So first, let's get this local axis and this assemble element. That's right. So I hope I will get this right. So these are my local axes here. I'm not going to explain this process of this change of bases into this local coordinate system very thoroughly, because I think it's worth it to focus on other parts of this problem. So just stay with me for 1 second. So first we have to deconstruct plane, and now we have to shift the x and y axis as we said before, because Karamba is defining the curvature around the axis, unlike a grasshopper. So let's construct the plane, and x becomes y and y becomes minus x. So okay, and now let's define the change of basis finally. Orient. So my global coordinates are the xy coordinates, that's fine, and my local coordinates I'm going to get from here. And now I just want to get the input vector, and since we are defining the curvature, as I say, around the axis, we are going to get yes, right, we are going to get the maximum direction, the vector of the maximum direction, key 2, like that. Okay, so now we should have our vectors with the curvatures in the right coordinates, but again we have this problem as before with the minus and plus signs. So we are going to fix that problem very easily, because we don't care whether the local axis pointing one direction or in the other. So let's use the absolute values for our vectors, and let's define this sign with the amplitude component directly from our curvature values. Okay, so now that should be it. So now we are ready to plug these values into our loads component. So initial strain, fantastic, and now these are my curvatures here. And again, we need our identifiers, and we need to graft these inputs so that its curvature works with one element. So those are my identifiers. Sorry, let me graph this guy before. And important, very important, don't forget to do this, please. So we have to flatten our output before connecting it into our assemble model component here. So okay, I think this is a bit of a mess, sorry, but I hope we are ready to go. So let me just hide this guy so we can see better our results later on. No, I didn't want to do that. And hide. So we are going to calculate our Karamba model right now, and since the faces or the sheets are more or less fixed, we don't need to use the large deformation analysis now, and we are going to use just the analysis with the first order, let's say. So now we just have to plug our model here, and it's very fast actually. So we can start getting some feedback from this component. So first we can see that the maximum deformation is 0.3 centimeters, which is quite low, at least in comparison with our previous example. So it looks like this geometry is quite efficient at least. And yes, the resulting force of gravity is 0, of course, because we don't have external loads. So let's see how our results look like. And first we want to get the model view component as before, but one second. But now, since we are dealing with shell elements instead of beam elements, we have to use the shell view component instead, like that. So we can now hide this guy here. So the first thing we can see, the deformation, of course, this is, so if we make double click here, we can choose the maximum values for our scale factors here, and the deformation we can see if we, sorry, let me put this guy here. So now we are seeing the final results of our problem, for our developable structure, and we are starting with the deformation. So first, let's display the colors of the deformation in this shell view component with this gradient, and we can also choose the scale of our deformation, so you can see that it's not that dramatic, that important, because we saw that the maximum deformation was 0.3 millimeters, and yes, it's not that dramatic. So the shape more or less is the same as the initial shape that we theoretically defined in Rhino. And if we want to get this information or this data regarding the deformations in more detail, we can get this legend graph, and we just have to plug these parameters here, and we can get values of our deformations here, which of course it's really low in the white areas, and it goes up to 3 millimeters in the more intense lila zones, like that. Okay, so that was everything regarding our deformations, I guess. So now we can take a look into the utilization, which is basically, let's take a look to the colors. So the utilization, it's the relationship between the forces in our elements and the strength capacity. But first, let's take a look at the colors. So we're seeing now the outer parts of our faces, the outer faces, let's say. So blue means tension and red means compression. And I think it makes sense, because if you can imagine that we have a planar sheet of poplar wood in this case, and we try to fold it in this way, we would get tension in the outer face, like we are getting that right now. And this face, had the curvature, let's say, in the opposite way as this one. So if we can imagine our sheet that we are trying to bend in this direction, it makes sense that we are getting this red color like here. And of course, since the curvature is lower in this face, this is more or less planar, I would say, these colors here are more intense. So, okay, that was a first analysis of our results regarding the utilization, but let's take a look into the exact values, let's say here. So we can see that we have up to 200%, which means that we are exceeding our capacity of our poplar wood by, I mean, the forces are double so high as the maximum value. So it means that we have to make something to that. And we can see that we are getting the more intense colors, or the maximum utilization, let's say in this area here. And we can see that it's the area in which the curvature is more pronounced, let's say. So now we have to decide how we can fix our structure. Of course, the first option would be to use another geometry with trying to avoid this pronounced curvature here. But in case that we are really happy with this geometry and we don't want to modify that, we could use a different approach. So what we can do as well, and it's very easy to do this with Karamba, is basically we can try to change this height parameter. So instead of using 1 centimeter thick plates or thick sheets, we can use 0.5 centimeters as thickness, so that our sheets are more flexible, let's say, and we don't get such high forces. So now we can get back to our utilization factors here, and we can see that we're basically inside of the strength capacity of our poplar wood. So that could be a really interesting approach, basically to use thinner sheets of poplar wood so that we can fold them into our geometry. So that was basically, that's how you analyze a developable structure with Karamba, and you can get that interesting feedback in order to make some design decisions before getting into the process of actually building our developable structures.